Welcome. We're looking at a fascinating article today that really, it completely reframes the whole AI conversation. For years, the spotlight was so bright on training.
Oh, absolutely. It was all about parameter counts, how huge the data set was, the sheer cost of the compute.
Exactly. It was this era of building the biggest, most powerful engine imaginable, but now that engine is built. We're in the
Mm.
deployment era, and the question isn't how to build it anymore. It's how do we run this thing efficiently?
Right. And the article we're discussing puts it so well. A trained model is just this massive binary blob of weights. It's all potential energy just sitting there.
And LLM inference is the spark that turns it into kinetic energy.
It is. It's the trigger.
But the core idea in this piece, and what really caught my eye, is that inference is, and I'm quoting here, surprisingly hostile to our current hardware. It's slow, it's expensive, it's a memory hog.
Yeah. If training was brute force, inference is, well, the author calls it an art form of optimization.
I love that. So today, that's what we're going to unpack. We're going to explore why it's so hard and look at the, frankly, genius techniques engineers are using to break through these bottlenecks.
Let's do it.
So let's start with the basics. People say inference is just next token prediction, but the article argues that's like saying driving a Formula One car is just turning the steering wheel.
It's a massive
That-
oversimplification.
Yeah.
Because when you actually submit a prompt, the process splits into two very distinct phases.
Okay.
The first one is the prefill phase. This is when the model takes your prompt, let's say it's 100 tokens, and it processes them all in parallel,
All at once.
all at once. And this part is actually really fast. GPUs, they excel at this kind of parallel matrix math. It's their bread and butter.
But then we hit phase two. The article calls it auto-regression or decoding. And this is where, the dream of parallelism just dies.
It completely collapses because to generate the second token, the model needs the first token. To get the third, it needs the second.
Yeah.
It's a serial, sequential lockstep.
So you have this hardware that's built for doing 10,000 things at once, and you're forcing it to do one thing, then the next, then the next.
That is the fundamental tension. And it's the source of almost every performance headache we're about to talk about.
So, okay, if it's sequential, why isn't it just instantaneous? I mean, we're talking about H100s, the most powerful chips on the planet.
And this is the most surprising point in the whole article, I think. The bottleneck isn't raw speed. It's not FLOPS floating point operations per second.
The GPU has plenty of horsepower.
Tons of it. The single biggest killer of performance is memory bandwidth.
Moving the data.
Just moving the data.
Yeah.
To generate that one single next token, the model has to load its entire set of weights, we're talking hundreds of gigabytes, from the GPU's memory, the HBM, into the cores.
And it does that for a single token, runs a quick calculation, and then what? It just discards them and loads them all over again for the next token.
Yes. That's why the analogy they use is so perfect. It's like trying to drink a giant milkshake through a tiny coffee stirrer. The powerful cores are just sitting there, idle, waiting for data.
Wow. Okay, so that physical reality immediately creates this huge trade-off that engineers have to deal with, right? The one between latency and throughput.
Exactly. Two sides of the same coin.
Latency is how fast I get my answer back as a single user.
And throughput is how many people, how many users the system can handle at the same time.
And the dilemma from a business perspective is that techniques that make one better often make the other worse.
Right. If you're building a chatbot for, say, real-time medical advice, you need latency to be as low as possible. You optimize for that single user's experience.
But if you're a big API provider, serving millions of requests,
You have to optimize for throughput.
Mhm.
Your goal is to keep that multi-million-dollar GPU cluster running at 100% capacity. Big batches help with that, but it means individual users might have to wait a little longer. It's a constant balancing act.
and tied directly into this whole memory problem is, well, the elephant in the VRAM, I guess, the KV cache.
Oh, yes, the KV cache,
Explain this, because it's a huge source of pain. It's the model's short-term memory, right?
pretty much. It stores key attention data, the keys and values, for all the tokens it's seen so far. That way, it doesn't have to reread the whole conversation from scratch for every new word.
So it's essential for context. But the problem is, it just grows and grows.
Linearly. The longer your conversation, the bigger the cache gets. For these new long context models, the KV cache can actually become bigger than the model weights themselves.
And when you have hundreds of users on one machine, all with their own growing caches.
You get memory fragmentation. It's like your VRAM gets filled up with these unusable Swiss cheese holes, as the article puts it.
Yeah.
And that's what leads to those dreaded out-of-memory errors that crash everything.
Okay, so the physics are tough, the architecture is a challenge, but the software layer on top of it all, That's where the real war for efficiency is being fought. And it's not one size fits all.
Not at all. There's a whole ecosystem of inference engines now, and each one has a totally different philosophy.
Let's start with the one most people probably know, Llama.cpp.
Llama.cpp is the people's champion. Its entire goal is accessibility. It's designed to run on anything, your MacBook with Apple Silicon, an old desktop with just a CPU. It's about democratizing access.
So that's for local hobbyist use. But if you're building a production API,
Then you're almost certainly looking at vLLM. It's the king of high-throughput serving. Its entire design is obsessed with memory efficiency and maximizing how many requests you can serve at once.
and its secret weapon is something called PagedAttention, which we'll get to.
We will. Then you have the speed demons, like Llama v2.
Right. This one's for a very specific crowd.
A very specific, very happy crowd. If you own a modern consumer Nvidia card, like a 3090 or a 4090, Llama v2 is tuned to squeeze every last drop of performance out of that specific hardware. Minimum latency is its only goal.
And finally, you have wrappers like Llama.
Yeah, Llama is all about user experience. Its main feature is just simplicity. It's like Docker for LLMs. You type one command, and you're running a model. It often uses Llama.cpp under the hood, but it hides all the complexity.
So the takeaway is clear. Your mission, whether it's local experiments or a global API, really dictates your choice of engine.
100%.
Okay, let's get into the art form of optimization, the actual techniques. We said memory bandwidth is the bottleneck, so the most obvious solution is make the data smaller.
Exactly. And that technique is called quantization.
So instead of using the standard 16-bit numbers the model was trained on,
You map them to smaller, lower precision numbers, usually 8-bit integers or even 4-bit. It's like taking a super high-resolution photo and saving it as a slightly lower quality JPEG.
it's a trade-off. You lose a little bit of fidelity.
A tiny bit. But the file size, the memory footprint, shrinks dramatically. A 4-bit model takes up only a quarter of the space of the original.
Which means you can run a much bigger, smarter model on the same consumer GPU.
Or you can serve 4 times as many users on your expensive enterprise GPU. And what's amazing is that with modern quantization techniques, the loss in accuracy is often, almost negligible for most tasks. It's a massive win for efficiency.
Okay, so that shrinks the model. But let's go back to that KV cache problem, the memory fragmentation, the Swiss cheese holes. You mentioned vLLM solves this with PagedAttention. How does that work?
It's such an elegant idea because it's borrowed directly from modern operating systems. Your OS doesn't give a program one giant chunk of memory. It gives it smaller, non-contiguous pages.
And PagedAttention does the same thing for the KV cache.
Precisely. It breaks the cache into these fixed-size blocks or pages. This completely eliminates that wasted, fragmented space. It means the engine can pack way more users onto a single GPU, which directly boosts throughput. It's a huge deal.
Okay, that's a memory hack. What about a speed hack? How do you cheat that sequential token-by-token lockstep?
This is one of my favorites. It's called Speculative Decoding. It's so clever.
It sounds like a cheat code.
It basically is. You use a very small, very fast draft model to just guess the next 3 or 4 tokens. It spits them out almost instantly.
And then the big, slow, powerful model comes in.
And it checks all 4 of those guesses at the same time, in parallel.
Ah, because checking 4 tokens in parallel is just as fast for the big model as generating 1 token serially.
You got it. And if the little model's guesses were right, you just got 3 or 4 tokens for the price of 1. You just skipped ahead in the sequence, massively reducing your latency. It's brilliant.
So we've got one last major optimization, and it's key for anyone trying to build a service at scale, continuous batching.
This one is the secret sauce for high throughput providers. The problem with normal or naive batching is that everyone in the batch is stuck together.
Right. So if I ask a simple, short question, I might get stuck waiting for the person in my batch who's, asking the model to write a novel.
And your request is finished, but your slot is still occupied. It's wasted time and wasted GPU cycles.
Continuous batching fixes this.
It does. It operates at the iteration level, so token by token. The moment your short request is done, the engine sees that open slot and immediately injects the next waiting user into the batch.
No waiting, no wasted space.
The GPU cores stay fully saturated all the time. It's the key to maximizing the efficiency of that very, very expensive hardware.
All these software tricks are amazing, but you can't escape the silicon. And while Nvidia is still the dominant player, some really interesting specialized hardware is emerging just for inference.
Yeah, we have to talk about things like language processing units, or LPUs. The approach Groq took is fascinating.
They didn't try to beat Nvidia at its own game of parallel processing.
No, they attacked the real bottleneck we identified, memory bandwidth. They designed a chip with a massive amount of super-fast on-chip memory SRAM, and they load the model weights right onto the chip itself.
So they basically eliminate that chip to the slower external memory.
And the results are just staggering. We're talking hundreds of tokens per second. It's so fast, it almost looks like a bug.
And on the consumer side, the real unsung hero has to be Apple's unified memory.
Absolutely. The fact that the CPU and the GPU share the same memory pool is a game changer for running large models locally.
Because you don't have that huge data transfer penalty.
Exactly. It's why you can run a 70 billion parameter model on a MacBook, which would have been completely unthinkable a few years ago without a rack of enterprise GPUs.
And all of this hardware innovation, it seems to be pointing in one direction for the future.
Edge computing.
No data center at all.
That's the dream for a lot of applications. Running these models directly on your phone, on your laptop, using specialized NPUs, it means you get zero latency and, maybe more importantly, total privacy.
The article we read suggested this cool paradigm shift, that the cloud will handle what it calls System 2 thinking.
Right, the really complex, deep, resource-heavy reasoning.
While your local device handles the instant, intuitive System 1 tasks, like a quick summary of an email or translating a sign on the fly, the intelligence is moving from the server farm right into your pocket.
It's a huge shift in thinking.
So if we just pull all this together, it feels like the story of AI has genuinely changed. The era of make it bigger is now being joined by this new, urgent era of make it faster, cheaper, and smaller.
And inference optimization is the bridge that connects AI's raw potential to its actual utility as a product people can use every day.
So for anyone listening who's building with these models, what's the actionable takeaway here?
I think it's that you can't treat the inference pipeline as a black box anymore. You have to understand these trade-offs. You have to know what KV cache is. You have to understand quantization.
So if you're a hobbyist,
Download a Llama or Llama.cpp. Seriously, just try running a 7 billion and then a 70 billion parameter model with 4-bit quantization. Feel the difference on your own hardware. It will make all of this concrete.
and if you're building for production,
Then you need to be studying vLLM, PagedAttention, and continuous batching. That is the state-of-the-art for high-throughput serving right now.
You know, the fundamental lesson from all of this seems to be that computing the data is easy now. Moving the data, that's the real 21st century bottleneck. So I'll leave you with this thought. Look around your own work, your own domain. Where are the virtual KV caches bloating your systems? What's your equivalent of speculative decoding waiting to be discovered? Go find that constraint.